Okay, so this part we're actually going to put two together. So we're going to do 5D and 5E, which are EM waves and the electromagnetic spectrum. Put them together because they're essentially the same thing. So if we actually introduce electromagnetic waves first, then what we need to know is that an EM wave, which stands for electromagnetic wave, is just a transverse wave. So you can see in the diagram here, we've done this already in Waves Chapter 4, a transverse wave which oscillates perpendicular to the direction of the wave. But in this case, it's not matter that's oscillating. So in all the waves we looked at that were transferred through matter, all the transverse waves even, the oscillations of the matter were perpendicular to the direction of the wave. Now EM or electromagnetic waves, they don't actually use matter to be able to transfer the wave or the energy because they can travel through a vacuum. So it's just electro and magnetic fields which oscillate perpendicular to one another and therefore transfer that energy and the information from one place to another, which can happen through a vacuum as well. So electromagnetic waves are all transverse waves. So the first similarity of all of these different types of EM wave, or they are all transverse. They all travel at the same speed in a vacuum. So if they're traveling through space, they will travel at the same speed, which is actually the speed of light. So the speed of light doesn't just refer to visible light, but it actually refers to all parts of the EM spectrum, or all EM waves, in a vacuum. Some of them may travel differently in different materials, just like the colours of the visible spectrum, which travel at different speeds through glass. But in a vacuum, they travel at the same speed. So a second similarity of all the EM waves is that they all travel at the same speed in a vacuum. Now, if we look at the electromagnetic spectrum specifically, so we're discussing EM or electromagnetic waves, but if we look at the spectrum, that just means that there are a range of different types of electromagnetic wave. All right, and the reason that there are different types is because they all have, and actually you look at this diagram, it shows you that the amount of waves for each one is getting smaller and smaller. That represents a change in wavelength and in frequency. So the reason there are different types of EM wave is because each type has a different range of wavelengths. So let's start at this end where we've got radio. Radio waves actually have the longest wavelengths. So for all EM waves, radio waves have the longest wavelength. And then we come through to microwave, which have a little bit shorter wavelength, a range of shorter wavelengths, infrared radiation, shorter wavelength, all the way through visible light, ultraviolet, X-rays, to gamma rays at the very other end of the EM spectrum, which have the shortest wavelength. So all EM waves have different wavelengths, and they start from radio waves with the longest, all the way through to gamma rays at the shortest. They all therefore have different frequencies, because if they have a different wavelength, they have a different frequency. So as the wavelength of these waves decreases, the frequency increases. So lowest frequency for radio waves, increasing frequency all the way along the spectrum to the highest frequency EM waves at gamma. So lowest frequency radio, highest frequency gamma, longest wavelength radio, shortest wavelength gamma. If we look specifically at the visible spectrum then, for the same thing, red, which is on the left side on this diagram, which is next to the infrared part of the spectrum, red actually has the longest wavelength, longer wavelengths this way. So red has the longest wavelength, violet has the shortest wavelength of the colours, and red has the lowest frequency and violet has the highest frequency. All right, we can also actually discuss the energy of each type of wave. So each EM wave has a different amount of energy. The lowest energy wave is radio, so lowest frequency wave have the lowest energy. So radio with lowest frequency have the lowest energy, all the way through to gamma with the highest frequency and therefore have the highest energy. And we'll find actually in the next section that the amount of energy that these EM waves can transfer has something to do with the dangers that they come with as well. So the more energy they have, they're more dangerous types of waves. So just again to summarize, really the EM spectrum is made of different types of EM wave, starting with radio, longest wavelength, shortest frequency, lowest energy, radio waves, microwaves, infrared, which is thermal energy or heat energy, visible light, ultraviolet, X-rays and gamma rays. They are all the different types of EM or electromagnetic wave. We said that they all are transverse waves, so all of the oscillations that take place in the EM fields is perpendicular to the direction, and they all travel at the same speed in a vacuum. Differences are different wavelengths, longest to shortest, different frequencies, lowest to highest, and different energies as well, lowest energy to highest energy. The only other things worth mentioning really is if we look at an image here that actually describes how these EM waves travel through the atmosphere. So one thing to note is that the band in the EM spectrum, the band that we humans can actually detect, which is visible light, okay, that has a very, very specific and quite a small range of frequencies and wavelengths. So if we go back to the EM spectrum, visible light was right in the middle. It was a tiny, tiny part of the whole spectrum of EM waves. And what's worth considering is the reason that we can actually detect those waves. Why can't we see in X-ray? Why can't we see in gamma? All right? And this image actually gives you the best explanation as to why. So the only real waves from the EM spectrum that make it all the way to the Earth through the atmosphere from the very top are visible light and radio. Obviously we get some infrared, which can make it quite far down, so we do get some heat making it all the way through the atmosphere. But in terms of ultraviolet, X-ray and gamma ray, almost none of those waves are making it to the ground. Over time things are changing. Obviously UV is becoming more and more prominent at the surface of the Earth. It's quite dangerous, but in general UV, X-ray, gamma, even infrared, micro, don't really make it through the atmosphere. So most of the EM waves in the spectrum are absorbed in the atmosphere somewhere, whether it's at the top or slightly further down. They're all absorbed before they actually reach the ground. Now visible light, almost all of it is actually reaching the ground, and therefore over time humans have evolved to be able to see through this part of the spectrum. Our eyes have evolved so that we can see these frequencies and wavelengths because it is the most abundant type of EM wave on the surface of the planet. So we can see it because we need it and because there is a lot of it. But X-ray would be a waste of time because there are no X-rays really coming through the atmosphere, so it wouldn't be useful for us to see in that part of the spectrum. Okay, so all the different types of EM wave which we looked at: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, longest wavelength to shortest, lowest frequency to highest, lowest energy to highest, and then obviously a little bit about why is it that we see in the visible. But other than that, that is what EM waves are and the different types of EM wave that we have.